In this video, we want to learn how to solve a system of ODEs using the eigenvalue method. This system is actually quite easy to solve, and in another video, I show you how to do it without using the eigenvalue method. Nonetheless, the purpose is to understand the eigenvalue method. So, in solving this, we want to let x be a vector with two components, x1 and x2. And then we know that if you take the derivative of x, you're going to get the derivative of each component as so. You are then going to go ahead and take and plug in these two values into here. And so you're going to get that this is 2 times x1, 3 times x2. Close it off. You then want to separate this into as many vectors as there are variables. So we have the variable x1, and then we also have the variable x2. So in order for this to make sense, you're going to need a 2 at the top and a 0 at the bottom. You're going to need a 0 up here and a 3 down here. What you're going to notice is that this is a linear combination of two vectors, so we can rewrite this as a matrix times the vector x1 and x2. So then, in the matrix, what we're going to have are the entries of the first vector for the first column, 2, 0. And then for the one on the right, we're going to have 0, 3. You can then write this as 2, 0, 0, 3 times the vector x. Awesome. So then, if you go ahead and look at the left, what you have here, and look at the right, what you have here, you can restate this question. Instead of writing these equations here, we could have just written solve this system of ODEs in the following form, where you have a 2, a 0, a 0, and a 3 times the vector x. So this is what we want to solve. So now that we have it in this form, what you want to do is you want to try solutions. So I want you to remember back in the day, not that long ago, before these were vectors. So first of all, let me change this to p times x. Back in the day, you had this. When x was just a variable, it wasn't a vector. P was just a constant, a number, times another variable, and we have a derivative on the left. How did you solve this? Well, one of the ways that you solve this is you tried the solution e to the lambda t. Well, that was our guess. That is what we tried, and then we try to solve for lambda. What is lambda? So in this case, let's go ahead and turn these back into vectors. So this is a vector, this is a vector, and P is again a matrix. So we want to try something similar. So x has to be a vector. So what we're going to do is we're simply just going to put a vector v. All right. So now we want to plug this in back to this equation and try to figure out what lambda is and what v is. So the goal is to, 1, find what lambda is. The second goal is to find what v is. Cool. So let's go ahead and do that. Let's go ahead and plug it into the equation. So in order to plug this in, what we need here is we need the derivative of x. So the derivative of this particular x is going to be v times lambda e to the lambda t. So then we go ahead and plug it in to the top here, and then we're going to get v times lambda e to the lambda t, and this is equal to p times v e to the lambda t. If you remember from last time, the next step was to divide out by e to the lambda t from both sides. If you do that, we're going to get v times lambda, which is equal to p times v. All right? The question has now turned into find such a lambda and find such a v such that this holds. Okay, well, what does this actually mean? Let's go ahead and move them over to one side. Well, if we do that, we're going to get 0. And remember, 0, I write 0, but 0 in reality is the 0 vector. I'm going to have p times v minus v times lambda. And we can factor out the p. So therefore, we're going to get p minus lambda times the identity times v. This should look familiar. In fact, let me go ahead and just highlight this at the top. When you saw this for the first time, you should have been like, hey, that reminds me of eigenvectors. V is going to be an eigenvector. And if you remember from linear algebra, we also require that v is not 0. Well, how do we guarantee that v is not 0? We take a close examination of this right here. If this matrix is invertible, so call this matrix B. If B is invertible, then what we could do to both sides is we could multiply by B inverse. And if we do that, we're going to get B inverse times 0, which is equal to B inverse times B times V. This reduces to V on the right, and on the left we get 0. This creates a problem. Remember, we don't want this. So we want solutions such that this is not invertible. So if we restrict ourselves to B being not invertible, we find such a solution. We find our eigenvectors. Well, all right. How do we guarantee that? Well, we want the determinant to be 0. So we set the determinant, now this is just the normal 0, of p minus lambda I to be not 0. Let's go ahead and remember what our matrix is. So if we go to the top, our matrix that we're working with, I'll go ahead and copy this matrix, bring it down, is going to be the one we created. Minus lambda times the identity. So we're going to get the determinant of 2 minus lambda, 0, 0, 3 minus lambda. You multiply this out, we're going to get 2 minus lambda times 3 minus lambda. Therefore, our eigenvalues are going to be 2 and lambda is equal to 3. All right. The next step is to find the eigenvectors corresponding to each one of these. So let's go ahead and begin with lambda is equal to 2. So we plug it into this, p minus our eigenvalue. So in this case, it's going to be 2 times the identity. And we want such a v such that this goes to 0. So filling in the blank using our matrix, we're going to get 0, 0, 0, and we subtract 3 minus 2, we're going to get 1 times V. So this matrix is pretty easy to solve. If it was more complicated, you can go ahead and do your row echelon operations on it. But for this case, what we're going to get here is that we're going to get that V2 is equal to 0 and that V1 is a free variable. This means that V1 can be anything you want. So we now write our eigenvectors. Our eigenvectors for corresponding with lambda is equal to 2 are of the form V1 and V2 is 0. We have infinitely many eigenvectors, but we only need one of them. So we can just choose V1 to be 1, and we will work with this one, 1, 0. Now, we do the same thing. We set 0 is equal to P minus 3 times the identity times V. So what we're going to get is on the top left, we're going to get 2 minus 3. And so then we're going to get negative 1. We're going to get 0, 0, and 0 times V. So what we have here is that V1 times negative 1 is going to be 0, while V2 is going to be a free variable. So we go ahead and write what our eigenvector is in this particular case. V1 is 0 and V2 is free, and we only need one of them, so we work with V2 being 1. So then what we're going to get here is the following. We have our vectors, but now the question is, how do we put this together with what we want? Remember what our solution looks like. x1 is going to be v times e to the lambda t. So what we have here is 1, 0 times e. And what was our lambda? Our lambda was 2t. So that's one of our solutions. Our second solution is going to be 0, 1 times e to our lambda, and our lambda was 3 and t times t. So these are two solutions. They are linearly independent, and since we're dealing with a 2 by 2 matrix, then all solutions are of the form are linear combinations. So C1 is a constant. Here's one vector. Are linear combinations of all of these. So we go ahead and write this out. C1 times 1, 0, e to the 2t plus C2 times 0, 1, e to the 3t. And if you want, you can go ahead and write this as a matrix. The matrix is going to be this times the vector C1, C2. And you're just going to replace here, these entries here are going to go below. So we're going to get e to t0. And on the right, we're going to get 0 e to the 3t. This matrix here is what we call the fundamental matrix. And sometimes it's denoted as capital X, not to be confused with lowercase. t. It's a function of t. It's a matrix. It's the fundamental matrix, while on the left is the vector.